Tonight, we're going to explore one of the most profound questions in the future of human spaceflight. Not whether we can send astronauts to Mars, but whether the first crew to walk that red desert will ever set foot on Earth again. Most people assume the hard part is getting there. After all, Mars is hundreds of millions of kilometers away. The journey takes months. The spacecraft must keep its crew alive in deep space, and then it has to land safely on another planet. But strangely, none of that may be the hardest part. Because once those astronauts are standing on the Martian surface, they face a challenge unlike anything humanity has ever attempted. They must launch from a world with no infrastructure, no rescue teams, no spare parts, and no second chances. If anything goes wrong, there is no backup plan waiting over the horizon. By the end of tonight, you're going to understand why returning from Mars may be far more difficult than reaching it. Why a mission that succeeds in every other way can still fail at the very last step. And why some engineers believe the trip home is the single most dangerous part of the entire journey. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Think about the way we normally explore Mars. When NASA's Perseverance rover landed in February 2021, nobody expected it to come home. That was never part of the mission. It rolled onto Martian soil, began its work, and will spend the rest of its existence there. The mission was designed that way from the beginning, and no one considers that a failure. It is simply how we explore when the only cargo that needs protecting is data. Change one variable. Put a human being inside that rover. Now the mission has a second half. That second half is where everything gets difficult. There is a moment in the history of spaceflight that feels, from this distance, like proof that we already know how to do this. Between 1969 and 1972, 12 astronauts walked on the moon. All 12 came home. The Apollo program launched from Earth, reached another world, and returned its crews safely. That record stands. And because it stands, it is easy to look toward Mars and assume the same logic applies. We did it before. We will do it again. Only farther. But that assumption is carrying more weight than it can hold. The moon is, in cosmic terms, practically next door. It sits a little under 400,000 kilometers away. A spacecraft can reach it in roughly 3 days. If something goes wrong, you are 3 days from home. The Apollo 13 crew proved that in April 1970, nursing a crippled spacecraft back across that short stretch of space. The proximity was not an accident of good fortune. It was load-bearing. Mars, at a typical mission distance, sits roughly 228 million kilometers away. Not a few days, months. And when you are there, you are there. No rapid return, no rescue mission that arrives in time to matter. But distance is not even the central problem. Distance is just the context. The real problem is gravity. Here is what the numbers actually say. To lift off the moon, you need to reach an escape velocity of about 2.4 kilometers per second. That is the speed at which a spacecraft can outrun the moon's gravitational pull and climb away into space. 2.4 kilometers per second. In rough human terms, that is fast enough to cross the distance between two neighboring cities in a single second. The moon's gravity is a gentle whisper. The Apollo Ascent stage was a small, almost fragile-looking vehicle. It worked. Mars has a firmer grip. To leave Mars, a spacecraft must reach 5.03 kilometers per second, more than twice the escape velocity of the moon. And that gap matters far more than the raw numbers suggest, because escape velocity does not scale linearly with the energy required to achieve it. The energy a rocket needs grows with the square of the velocity. Roughly speaking, escaping Mars requires not twice the energy of escaping the moon, but something closer to 4 times as much. Not a bigger Apollo Ascent stage, a fundamentally different vehicle. And then there is Earth waiting at the far end of the journey. To come home, a spacecraft accelerating from Mars must eventually deal with Earth's own escape velocity of 11.2 kilometers per second. This time in reverse, bleeding off that speed through the atmosphere in a corridor measured in fractions of a degree. Miss the corridor too high, and the ship skips off the atmosphere back into space. Miss it too low, and the heat becomes unsurvivable, But the reality was different. All of this, the escape velocities, the corridor, the energy demands, is solvable in principle. Physics gives us hard numbers, and hard numbers can be engineered against. The real trap is not the speed. The real trap is the question underneath the speed. How, where, and with what? On Earth, a rocket reaches escape velocity because it carries fuel loaded at a launch facility, assembled by thousands of engineers, tested over years, and ignited at a moment of a collective readiness. The infrastructure behind any launch is staggering. It does not fit in a spacecraft. At Mars, the crew standing on the surface and preparing to leave is standing 228 million kilometers from the nearest fuel depot, the nearest engineer, the nearest spare part. Everything needed to generate 5.03 kilometers per second of velocity must either arrive with the crew on the outbound trip or be manufactured from Martian resources after landing. Both options carry costs that grow quickly when you trace them backward through the rocket equation, a relationship between fuel mass and payload mass that will become very important very soon. Mars does not reach out and prevent the return. It does not act against the crew. It simply sits there, large and old and unbothered, exerting the same gravitational pull it has exerted for 4 billion years. That pull does not negotiate. It does not diminish because the mission is important or the crew is brave. It is indifferent in the way that only a planet can be indifferent. And escaping that indifference from the surface with no outside help is the problem that every return mission to Mars must solve before any human being sets foot there. The escape velocity is only the beginning of it. Let's think about what coming back actually requires. The previous section named the rocket equation. Now it is time to feel what it does. The Tsiolkovsky rocket equation is a law of physics named after Konstantin Tsiolkovsky, a Russian scientist who worked out its implications more than a century ago. It describes the relationship between the mass of fuel a rocket carries and the change in velocity that rocket can achieve. The relationship is not linear. It is not even close to linear. It is exponential. Every extra unit of velocity you need from a rocket demands a disproportionately larger amount of fuel. And every kilogram of fuel you add weighs something, which means you need more fuel to carry it, which means you need more fuel to carry that fuel, which means you need more fuel again. The phrase for this is a brutal mathematical pyramid scheme. You want to carry fuel to Mars for the return trip. That fuel has mass. The mass of that fuel must be lifted from Earth, which requires fuel. The fuel required to lift the return fuel also has mass, which requires more fuel to lift. The pyramid builds quickly. The numbers do not stay manageable, they compound. This is the reason engineers and mission planners talk about the rocket equation the way they do, with a kind of hushed respect. It is not simply a formula. It is a constraint. A wall that gets taller the harder you push against it. The answer was stranger than expected. The wall does not announce itself politely. You do not notice it gradually. You plan a mission, you trace the fuel requirements backward, and suddenly the numbers are not double what you expected. They are not triple. They are orders of magnitude beyond what the launch vehicle can carry. The rocket equation has a way of collapsing assumptions quietly, and then revealing the wreckage all at once. Which is why the most honest illustration of what human return from Mars actually demands is not a starship. It is something much smaller. NASA's Mars Sample Return Program has spent years and billions of dollars engineering a vehicle called the Mars Ascent Vehicle, the MAV. The MAV is not large. It stands roughly 3 meters tall. It weighs roughly 450 kilograms. To put that in proportion, it is about the height of a standard doorway and less massive than a grand piano. This is not a vehicle designed to carry a crew. It is not designed to carry supplies or equipment or emergency reserves. Its entire purpose is to lift a single sample container, roughly the size of a basketball, filled with rock and soil collected by the Perseverance rover, from the Martian surface into a low orbit where another spacecraft can retrieve it. A basketball of rocks. That is the payload. Years of engineering, billions of dollars. Technology that, as of this recording, does not fully exist yet. The precise propulsion systems the MAV requires are still being developed and tested. And the payload, at the end of all that effort, is a handful of Martian dust. This is not a criticism. The science inside that basketball could reshape our understanding of whether Mars ever supported life. Every gram of that sample matters. But the scale of the effort required to return even this tiny mass from the Martian surface should give anyone pause who imagines a human crew doing something similar. If the MAV, 3 meters tall and carrying no people, pushes the edges of what current engineering can achieve, then the vehicle required to lift even a small crew into Martian orbit is not a scaled-up MAV. It is a fundamentally different class of machine, one that does not yet exist. The MAV would be the first object ever launched from the surface of another planet. The first. Every rocket ever built, every payload ever lifted, every orbital insertion in the history of spaceflight has happened from Earth or from Earth orbit. No one has ever successfully launched from another planetary surface. The MAV, if it flies as planned, will be the first time that happens, and it will be carrying a basketball of gravel. But the rocket equation alone does not fully explain why returning from Mars is so punishing. There is a second constraint, and it works against the first. Mars offers almost no assistance during landing or launch. The reason is its atmosphere. Earth's atmosphere at sea level exerts a pressure of roughly 100,000 pascals. That air resistance is what allows parachutes to work, what allows spacecraft to bleed off velocity through atmospheric braking, what reduces the fuel required to slow down during re-entry. Mars's atmosphere exerts a pressure of roughly 610 pascals, less than 1% of Earth's. To get a sense of that thinness, imagine the atmosphere at an altitude of more than 30 kilometers above Earth's surface, far above where weather systems form, far above the ceiling of any commercial aircraft. That is the air a spacecraft encounters when it arrives at Mars. Not at altitude, at the surface. Parachutes work poorly in such thin air. Atmospheric braking works poorly. The friction and drag that Earth uses so efficiently to slow an incoming spacecraft, to convert speed into heat and distribute it across a heat shield over many seconds, barely applies on Mars. Engineers use parachutes during Mars landings, but those parachutes can only do a fraction of the work they would do on Earth. The rest must be done by rockets. Retro rockets firing against the direction of motion, burning fuel, adding mass requirements to the mission before it ever arrives. And at launch, it is the same problem in reverse. Earth's atmosphere is thick enough to be a nuisance during ascent, creating drag, but it is also thick enough to support the aerodynamic surfaces that help stabilize a rocket's climb. Mars offers neither the drag on the way up, nor the braking on the way down. Rockets do the work in both directions. Fuel is consumed both landing and launching. The pyramid builds from both ends. This is the loop the rocket equation creates on Mars. The thin atmosphere demands more rocket power at landing. More rocket power requires more fuel. More fuel has more mass. More mass requires more launch capability. More launch capability requires more fuel. The equation folds back on itself, and each fold multiplies the cost. The rocket equation is not a problem that creativity or courage resolves. It is not a problem that better training or better engineering fully eliminates. It is a mathematical relationship between mass and velocity, and Mars, with its gravity and its near-absent atmosphere, sits at exactly the point on that relationship where the costs become severe. And that is before considering what the crew needs to survive for the months between landing and launch. There is a way out of the loop. It requires looking at what Mars already has. Mars's atmosphere is thin. We established that. But thin does not mean empty. The atmosphere is 95% carbon dioxide, almost no free oxygen, almost no ready-made oxidizer. From the standpoint of a rocket engineer, that sounds like a dead end. But carbon dioxide is not nothing. Carbon dioxide is carbon and oxygen, chemically bound together, and if you can pull those elements apart, you can make something useful from what would otherwise just be a problem. This is the chemistry that makes in-situ resource utilization possible. In-situ resource utilization means using what is already at your destination to supply what you would otherwise have to carry. For a Mars return mission, the critical target is oxygen. Not just for breathing, for burning. Nearly every rocket fuel combination we rely on uses oxygen as the oxidizer, the chemical that lets the fuel combust. The space shuttle's main engines ran on liquid hydrogen and liquid oxygen. The Falcon 9 burns RP-1, a refined form of kerosene, with liquid oxygen. No oxygen, no combustion. No combustion, no ascent. And if you cannot produce oxygen on Mars, you are back to the pyramid. Every kilogram of oxygen not made on the surface is a kilogram that had to ride the whole way from Earth, compounding the mass at every stage. So the question becomes, can you actually pull oxygen out of Martian air? In April 2021, a device the size of a car battery answered that question. It is called MOXIE, the Mars Oxygen In-situ Resource Utilization Experiment. It rides aboard the Perseverance rover, tucked into the rover's chassis, modest in scale and extraordinary in function. The process is sometimes described as a reverse breathing process, which is a useful analogy. When a human breathes, the body takes in oxygen and releases carbon dioxide as a byproduct. MOXIE runs the same exchange in reverse. It pulls in Martian air, heats it to around 800 degrees Celsius, and at that temperature breaks apart the carbon dioxide molecules. The oxygen atoms separate out. The carbon monoxide, the leftover byproduct, is vented back into the atmosphere. What remains is O2, oxygen, made on another planet from the air of that planet right now as you read this. That is not science fiction. That is an operating machine on the surface of Mars. But here is where it gets strange. The numbers tell a different story once you look closely. MOXIE produces 6 to 10 grams of oxygen per hour. That is a real number, a confirmed output, a genuine achievement. And against the scale of what Mars return actually requires, it is almost invisible. A human being needs roughly 840 grams of oxygen per day just to breathe. MOXIE, running continuously for an entire day, would produce somewhere between 144 and 240 grams. Less than a third of what one person needs to stay alive. A fraction of what a return rocket would need to fly. A rocket does not breathe, it consumes tons of liquid oxygen, not grams, tons of fuel to combust against that oxygen. The quantities involved in a crewed Mars ascent are not in the same order of magnitude as MOXIE's output. They are not within 2 orders of magnitude. The gap between what MOXIE demonstrates and what a return mission demands is so wide that it is easy to misread what MOXIE actually proves. What MOXIE proves is the concept. The chemistry works. The mechanism works. You can pull oxygen from Martian air using electrochemical reduction at high temperature. That part is solved, not theorized, not modeled. Solved on the surface of Mars with hardware that has been running since 2021. What MOXIE does not prove is the engineering at scale. Producing grams per hour and producing tons per month are not versions of the same problem. They are different classes of engineering entirely. A MOXIE-scale device is a laboratory demonstration. A rocket-grade oxygen production system would require machinery orders of magnitude larger, drawing far more power, operating continuously for months, without failure, in Martian dust and cold and radiation. That system does not exist. The design does not fully exist. The power infrastructure to run it does not exist on Mars. Every one of those gaps represents an engineering challenge that has not been climbed. This is the suspended note the concept lands on. We have proven that making oxygen on Mars is possible. We have not proven that we can make enough of it, fast enough, reliably enough, to fuel a human return. The proof of concept and the proof of capability are not the same thing. MOXIE is the first. The second is still ahead. And the oxygen is only one side of the fuel equation. The other side of that equation is a fuel. And the fuel problem connects directly to a plan that is already in motion. Not a proposal, not a concept study. A mission that has been building since Perseverance touched down in Jezero Crater in February 2021. Right now, at this moment, a rover is driving across the floor of an ancient lakebed, drilling cores from the Martian surface, sealing them into small metal tubes, and caching them at precise locations on the ground. The samples are waiting. They have been waiting for years. The question is how to bring them home. This is the Mars Sample Return Campaign. NASA and the European Space Agency are working together to do something that has never been done in the history of spaceflight. Bring physical material from another planet back to Earth. Not data, not photographs, not radio signals, actual matter, scooped from Martian bedrock, carried across hundreds of millions of kilometers, and landed intact in a laboratory. The plan requires 4 spacecraft working in sequence across more than a decade. Each step depends on the one before it. None of them can fail. Here is how it works. A future spacecraft, the Sample Retrieval Lander, descends to the surface near Jezero Crater. It carries 2 pieces of hardware that will do the actual retrieving. The first is the Mars Ascent Vehicle, introduced in an earlier part of this story, the small rocket, the first machine ever designed to launch from the surface of another planet. The second is a pair of small helicopters, built on the design of Ingenuity. Ingenuity was the first powered aircraft to fly on another planet, a small rotorcraft that lifted off the Martian surface in April 2021 and flew in air roughly 70 times thinner than the air at sea level on Earth. The fact that it flew at all was considered remarkable by the engineers who built it. The helicopters carried on the Sample Retrieval Lander are its successors. Their job is backup retrieval. If the rover cannot transfer the sample tubes to the MAV directly, the helicopters will fly to the cached locations, pick up the tubes, and carry them back. Once the samples are loaded, the MAV ignites. Think about what that sentence means. A rocket fires on the surface of Mars. For the first time in history, something built by human hands launches from the ground of another world. The MAV climbs through the thin Martian atmosphere, accelerating to the velocity needed to reach orbit. It carries almost nothing except the sample container, a few hundred grams of Martian rock. Its entire purpose, all of its engineering, all of its fuel, is to lift that small mass to orbital altitude and release it. In orbit, the sample container is traveling at roughly 4 kilometers per second. That is fast enough to circle Mars completely in a few hours, and it is alone up there. No crew, no guidance system capable of returning it to Earth on its own, no second chances. This is where the second half of the ballet begins. The European Space Agency's Earth Return Orbiter is already waiting in Mars orbit. It has been looping around the planet, waiting for the MAV to deliver its payload. Now it must close the distance, match speeds with a small metal canister traveling at 4 kilometers per second, and capture it. This is orbital rendezvous at a precision that has never been attempted, between spacecraft from 2 different agencies, in orbit around a planet where a round-trip radio signal takes up to 40 minutes. There is no real-time guidance from Earth. The rendezvous happens autonomously, guided by software and sensors alone. Once captured, the Earth Return Orbiter seals the sample container inside a larger protective capsule and begins the cruise back to Earth. Months of travel, then atmospheric entry, then landing. This would be the first spacecraft to make a complete round trip between Earth and Mars. The phrase that keeps appearing in mission documents is cosmic ballet. Every step must be choreographed precisely. Every handoff must work. The MAV must reach the right orbit. The Earth Return Orbiter must intercept correctly. The return capsule must survive entry. If any single step fails, the chain breaks. There is no rescue possible. There is no crew that can go outside and fix a problem. There is no second launch window that doesn't add years to the timeline. Every movement in the sequence is load-bearing. Now consider what this entire choreography is designed to retrieve. The samples Perseverance has been caching come from rock layers that formed when Jezero Crater was a lake. Roughly 3.5 billion years ago, water flowed into that basin from a river delta. Sediment accumulated. Organic chemistry may have had time to begin. These samples are time capsules from a period when Mars may have had a thicker atmosphere, liquid water on the surface, and conditions that we associate on Earth with the emergence of life. The question those samples might answer is the oldest question in planetary science. Are we alone? Not in the abstract sense of wondering about distant galaxies. In the immediate chemical sense of asking whether life, or its precursors, or at least conditions compatible with its origin, ever existed in the same solar system where we developed. The answer is not in the data Perseverance transmits. It is in the physical material, in the molecular structure of the rock, in isotope ratios that no instrument on Mars can measure with sufficient resolution. The sample has to come home for the question to be answerable. That is the scientific case for what is about to follow. The cost estimate for Mars sample return sits between $8 and $11 billion. The earliest realistic completion date is in the 2030s. All of that money and time will return approximately half a kilogram of Martian rock, 500 grams, roughly the weight of a small water bottle. The picture did not hold. The comparison that puts that figure in context is not the cost of other robotic missions. It is Apollo. The Apollo program returned 382 kilograms of lunar samples across 6 landings, hundreds of kilograms versus half a kilogram. The difference is not a reflection of ambition or caution. It is a reflection of distance. The moon is 3 days away. Mars, at its closest approach, is months away. And the journey home costs more in energy and time than the journey out. Getting half a kilogram from Mars will cost more, take longer, and require more coordinated engineering than getting hundreds of kilograms from the moon. Not a simpler version of the same problem. A fundamentally harder one. And this is the flaw. Mars sample return is the minimum case. It is robotic. It carries no crew. It requires no life support, no food, no water, no medical systems, no radiation shielding designed for human biology. The mass being returned is measured in grams. Every one of those engineering challenges compounds by orders of magnitude the moment a human being is added to the return mission. The cosmic ballet is the lower bound. What comes after it is something else entirely. Now imagine the cargo is not rocks. The mass being returned in the sample mission is half a kilogram. That number has weight. It represents billions of dollars, a decade of engineering, and a sequence of spacecraft so precisely choreographed that a single failure anywhere in the chain ends the mission permanently. And that is for half a kilogram of rock. Now imagine the cargo is a crew. A crewed Mars mission must return human beings. That means returning the suits they wear on the surface, the equipment they depend on, the life support systems that keep them alive, the food and water for a return voyage of 6 to 9 months, and the radiation shielding required to survive deep space for that entire duration. NASA has studied what this actually requires. The answer is staggering. Total mass assembled in low Earth orbit, just to send a crew to Mars and bring them home, could exceed 400 tons. That is roughly the mass of a fully loaded cargo ship. Not a spacecraft, a ship, sitting in orbit before the mission even departs. But something was wrong. You cannot launch 400 tons to Mars on a single rocket. You cannot launch it on 2 rockets. You can barely begin to imagine the parade of launches required to assemble that kind of mass in orbit, transfer it to Mars, and then somehow have enough fuel remaining to bring people home. But the deeper problem is not the launches. The deeper problem is the return fuel. Think about what that means in practice. Every kilogram of propellant needed to lift a crew off the surface of Mars must either travel all the way from Earth or be manufactured on Mars itself. Carrying it from Earth is essentially impossible at the scale required. The rocket equation does not forgive you for adding mass. Every kilogram of return fuel you pack means more fuel needed to carry that fuel to Mars, which means more fuel needed to carry that fuel's fuel, and the pyramid builds until the mission collapses under its own requirements. The math does not offer a workaround. Carry the fuel from Earth, and the mission cannot fly. Which means the only option remaining is to manufacture the fuel on Mars before the crew arrives. Not preferred. Not one option among several. The only option. This is what engineers call in-situ resource utilization, or in-situ. The concept has a simple version, live off the land. Instead of carrying everything you need from Earth, you use what the destination provides. Mars, it turns out, provides 2 key ingredients. The atmosphere is nearly all carbon dioxide, about 95% of it, and water ice exists beneath the surface and in the polar caps. Both of these are raw materials for rocket fuel. The chemistry works like this. You take water ice, melt it, and pass electrical current through it. The water splits into hydrogen and oxygen. You capture the atmospheric carbon dioxide. You combine the hydrogen and carbon dioxide in a chemical process that produces methane. Methane and oxygen, burned together, make excellent rocket propellant. Not adequate propellant, not a fallback option. The same propellant combination powering the Raptor engines that SpaceX uses on its Starship spacecraft, which are among the most powerful rocket engines ever built. The plan that SpaceX has outlined for Mars follows this logic directly. Starship lands on Mars with mostly empty propellant tanks. It sits on the surface while automated systems draw carbon dioxide from the atmosphere and water from beneath the ground, run the chemistry, and fill the tanks. This process takes not days, but months, possibly years, depending on how large the crew is and how much propellant the return journey requires. Only after the tanks are full does the crew launch. But now, consider where all of this chemistry must actually happen. Mars has an average surface temperature of -63 degrees Celsius. That is colder than the interior of Antarctica in winter. The temperature swings between day and night are roughly 100 degrees Celsius, which means the machinery must cycle through extreme cold and relative warmth every single Martian day without failing. The atmosphere is too thin to breathe. A person exposed to the Martian surface without a suit would lose consciousness in seconds. Dust storms can grow large enough to cover the entire planet, blocking sunlight for weeks and coating every surface with fine abrasive particles. And the radiation levels on the Martian surface, unshielded by the thick atmosphere and magnetic field that protect Earth, would be illegal for a worker to receive in most countries on Earth. That is the operating environment for an industrial-scale chemical plant running without a crew present, because the plant must run before the crew arrives. That is the sequence. You send the propellant manufacturing equipment first. You send it years in advance. It sits on the surface of Mars, completely unattended, operating in conditions that would destroy unprotected machinery on Earth, and it must run reliably enough to fill tanks sufficient for a human return journey. If it fails, the crew cannot leave. They have no backup fuel depot. There is no cargo flight that can bring them more propellant in time. The manufacturing must work. And then, the crew lands. They land farther from home than any human being has ever been. Not slightly farther, by an immense margin. And their first major task is not exploration. It is not science. It is to verify that the fuel factory is running and that the tanks are filling as planned. Because until those tanks are full, they are not visitors to Mars. They are stranded on Mars. That image matters. Hold it for a moment. 6 to 9 months from Earth, by the fastest available trajectory. No rescue possible at the scale required. And the first thing you do after landing is check on the chemical plant. The chemistry of ISRU, as we saw with MOXIE, has been demonstrated. The concept is not speculative, but a small device producing grams of oxygen per hour inside a rover is not an industrial fuel plant running continuously on the Martian surface for 2 years. The gap between those two things is the gap between knowing that fire exists and building a power grid. And the fuel factory is only one of the problems waiting on the surface. The crew is on the surface, the tanks are being filled, and every second they stand there, something is passing through them. Not a metaphor, a physical fact. High-energy particles, moving at fractions of the speed of light, are passing through the walls of the habitat, through the crew's bodies, through the nuclei of their cells, through the strands of their DNA. They cannot feel it. There is no sensation. There is no warning. The damage accumulates quietly, the way interest compounds on a debt you are not watching. On Earth, we live inside two invisible shields. The first is the atmosphere itself, roughly 100 kilometers of air pressed down by gravity. That column of gas absorbs and deflects the majority of the high-energy particles that rain down on the planet continuously. The second shield is the magnetic field, a vast, invisible structure generated by the movement of molten iron deep inside the Earth's core. It extends tens of thousands of kilometers into space in every direction. Most of the dangerous particles that reach the inner solar system never make it through. They are deflected, trapped, redirected. The auroras visible near the poles are a clue. They are what happens at the small gaps in that shield, where particles slip through and collide with the upper atmosphere, releasing light, brilliant, beautiful light, a visible reminder of an invisible protection most people have never thought about. Mars has neither of those things. The magnetic field died billions of years ago. The core cooled. When that happened, the dynamo effect stopped. The dynamo effect is the process by which a rotating, convecting liquid metal core generates a magnetic field, the same way an electrical generator creates current from spinning metal. When Mars lost its molten core movement, it lost its generator. The field collapsed. The atmosphere thinned over subsequent billions of years as solar wind particles, no longer deflected, stripped it gradually away. What remains today is not a shield. It is essentially nothing. And what that means for a crew on the surface is that Mars radiation levels run approximately 250 times higher than what humans experience standing on the surface of Earth. Something else was happening. The surface of Mars is not even the most dangerous part of the journey. During the cruise phases, the interplanetary transit out and the transit home, the spacecraft is farther from both Earth and Mars. It has no planetary body nearby to serve as any kind of partial shield, and it has no magnetic field around it. The vehicle walls provide some attenuation, but the primary threat in deep space is not something walls can stop easily. It is cosmic rays, not the solar radiation that causes ordinary sunburn. Cosmic rays are something fundamentally different. They are particles, primarily protons and atomic nuclei, accelerated to enormous velocities by supernovae, neutron star mergers, and other violent events scattered across the galaxy. They arrive from every direction. They have been traveling, in some cases, for millions of years before they arrive at the spacecraft. When a cosmic ray particle hits a thick material, it does not simply stop. It produces secondary radiation, a cascade. The original particle collides with atomic nuclei in the wall material, and those collisions generate a spray of new particles, pions, neutrons, gamma rays that spread in all directions. In many configurations, this secondary shower is more damaging to biological tissue than the original particle would have been if the wall had not been there at all. This is not a theoretical quirk. It is one of the central engineering challenges of deep space radiation shielding, and it has no clean solution. More mass does not always mean more protection. The relationship is complicated in ways that are still being studied. Now look at what the cumulative dose across a full Mars mission actually adds up to. The outbound cruise alone, 6 to 9 months of transit, delivers roughly 300 millisieverts of radiation to the crew. To put that in context, the United States limits occupational radiation workers, people who work professionally around radioactive materials, to 50 millisieverts per year. The outbound cruise delivers 6 times that before anyone sets foot on the surface. A single CT scan delivers roughly 10 millisieverts. 6 months in transit is the equivalent of approximately 30 CT scans worth of radiation, spread continuously, day after day, with no pause and no recovery. Then the crew arrives on the surface. Even inside a shielded habitat, even with whatever protection the structure provides, the surface stay adds another roughly 300 millisieverts over the approximately 18-month wait for the return window. Then the return cruise. Another 6 to 9 months. Another dose comparable to the outbound trip. Add it together. A full mission, outbound transit, surface stay, and return carries a total radiation exposure that may exceed 900 millisieverts, possibly more depending on solar activity. NASA's career radiation limit is designed to keep the lifetime increase in cancer risk below 3%. A Mars mission, by current best estimates, would exceed that limit. Not approach it, exceed it. And cancer risk, serious as it is not the only concern. High-energy cosmic ray particles, the heavy nuclei in particular, pass through human tissue differently than ordinary radiation. They can strike neurons directly. Animal studies have shown that chronic exposure to the kind of cosmic ray environment a Mars crew would experience produces measurable changes in the central nervous system, possible effects on memory, possible effects on cognition and decision-making, possible acceleration of degenerative neurological conditions. The research is ongoing. No human being has ever been exposed to this level of radiation for this duration. The long-term effects are not known. That sentence is not a reassurance. It is an acknowledgement that the answer does not yet exist. The engineering response to radiation is shielding, and shielding returns us immediately to the problem we have been circling throughout this entire mission: mass. Water absorbs radiation reasonably well, and a crewed Mars mission needs water in large quantities regardless. So, one approach is to route the water storage around the living quarters, using the tanks themselves as shielding material. Hydrogen-rich materials like polyethylene, a dense plastic used in everything from cutting boards to pipes, provide better shielding per kilogram than aluminum. Martian regolith, the loose soil and rock on the surface, is available in effectively unlimited quantity and can be piled around habitats for additional protection. These are all real options under active study, but every kilogram of shielding material added to the spacecraft is a kilogram that must be accelerated to interplanetary velocity and then decelerated into Mars orbit. The rocket equation does not care whether the mass is crew, food, equipment, or lead sheeting. It treats all mass the same way. More shielding means more propellant. More propellant means more mass to accelerate. And the pyramid builds again, the same way it built for fuel, for food, for every other consumable this mission must carry. There is no resource on a deep space transit that arrives for free. Apollo astronauts were exposed to deep space radiation for approximately 8 days total. That is not a difference in degree from a Mars mission. It is a difference in kind. 8 days against 900. A comparison between a sprint and a years-long crossing of open water, with no harbour anywhere between departure and arrival. Radiation does not pause when the crew sleeps. It does not pause during meals, during maintenance, during the careful, patient work of keeping an industrial fuel plant running on a cold and airless plane. It accumulates. Every day adds to what came before, and when the crew finally lights the return engines and begins the long transit home, it will still be accumulating. The tanks will be full. The fuel factory will have done its work, and the crew will be carrying something invisible with them that no factory can remove. The radiation problem has no clean solution, only trade-offs, and those trade-offs touch everything else on the mission. The mass of the shielding touches the fuel budget. The fuel budget touches the rocket equation. The rocket equation touches the ISRU timeline. The ISRU timeline touches how long the crew must stay, and how long the crew must stay increases the radiation dose. Everything connects to everything else on this mission, and radiation is not the last place that circle closes. Time on a Mars mission is not neutral. The same months that are writing invisible damage into the crew's DNA are also writing visible damage into the machines. The seals are drying, the electronics are absorbing radiation, the surfaces are being slowly pitted by micrometeorites too small to see, and the planets are moving. They are always moving, and the window they create together does not stay open. Think about what that means in concrete terms. Earth orbits the Sun in 365 days. Mars takes 687 days. These are not synchronized cycles. They are two runners on different tracks, moving at different speeds, their relative positions constantly shifting. Most of the time, they are not in a geometry that allows efficient travel between them. The most fuel-efficient paths between planets are called Hohmann transfer orbits, curved trajectories that use the minimum amount of propellant by following the natural curvature of the solar system. But a Hohmann transfer only works when the planets are in the right alignment to begin with. And that alignment occurs only once every 26 months. 26 months. That is the return launch window, not a flexible target, not a range of dates the crew can negotiate. A narrow corridor of orbital geometry that arrives, stays briefly, and then closes. If the crew misses it, they do not wait a few weeks. They wait 2 more years on a planet that has already been depleting their supplies and accumulating radiation dose in their bodies every single day. But the reality was different. Missing the window is not just an inconvenience, it is a cascade. 2 more years of food consumed, 2 more years of water recycled, of filters wearing, of equipment running past its designed operational life. 2 more years of radiation dose accumulating on top of what the surface stay already delivered. And at the end of those 2 years, the crew still has to launch. They have to do everything the mission required, except older, more depleted, and with equipment that has been running for twice as long as planned. There is an alternative. A less efficient trajectory that does not depend on optimal planetary alignment. But that path consumes far more fuel, and the mission has only what it has. The ISRU plant was designed to fill the tanks for a specific window, a specific trajectory, a specific fuel budget. Asking it to fill larger tanks for a harder path means running the plant longer, consuming more power, tolerating more risk of failure. The margins that were already razor thin become thinner still, and the journey itself is not fixed. The duration of the return cruise varies by window. Some alignments give a 6-month trip. Others stretch to 8 or 9 months. Which window you launch in determines how long the crew spends in transit, which determines how much additional radiation they absorb, which feeds back into the health accounting that has been running since they left Earth. Every variable connects to every other variable. None of them can be decided in isolation. Now comes the precision problem. You do not aim for where Earth is when you depart. You aim for where Earth will be when you arrive. 6 or 8 or 9 months from now, Earth will have continued its 365-day orbit. It will be in a completely different position. A tiny error in the departure angle compounds across hundreds of millions of kilometers. Not a small deviation. A trajectory that misses Earth entirely and continues into permanent solar orbit. The calculation has to be right before the engines ignite. Think of throwing a football not to where a receiver is standing, but to where that receiver will be running in 3 seconds. Now scale the throw to the size of the inner solar system. That is the precision required for a Mars return trajectory. It is achievable, but it is not forgiving. Mission Control does not simply set the course and wait. Throughout the return cruise, ground teams track the spacecraft continuously via radio signals and antenna arrays, calculating the small deviations that accumulate over time as gravitational influences nudge the vehicle off course. When the deviation reaches a threshold, they command a trajectory correction maneuver, a brief thruster firing that nudges the spacecraft back toward the correct path. Apollo performed several of these on its lunar missions. A Mars return would require more given the longer journey and tighter margins. Each correction is a small adjustment. Each one also burns fuel, and the fuel cannot be replenished once the spacecraft has left Mars. The mission planner therefore faces a continuous trade-off. Correct often, and you preserve precision, but drain reserves. Correct rarely, and you preserve fuel, but risk accumulating error that becomes harder to fix later. There is no option that carries no cost. Every decision spends something that cannot be recovered. The spacecraft making these corrections is not the craft it was. That is the part most people do not picture. We imagine the return vehicle as the same machine that will one day bring the crew home, sitting pristine on the Martian surface, waiting. The reality is different. It has been sitting on Mars for months, possibly more than a year, in conditions that test materials in ways no Earth laboratory fully replicates. The temperature swings alone are brutal. Days swing roughly 100 degrees Celsius from peak to trough. Seals that were designed to flex and hold begin to dry and stiffen. Metals contract and expand through cycle after cycle. Lubricants and moving parts behave differently at temperatures far outside their design range. Electronics that absorbed radiation during the transit to Mars continue absorbing it on the surface. And then there is the dust. Martian dust is not like ordinary dirt. It is extraordinarily fine, with a texture closer to talcum powder than to anything granular. It carries an electrostatic charge, which means it clings to surfaces rather than settling and brushing away. It works itself into mechanical assemblies, into gaps between components, into places where dust was never supposed to reach. And it contains perchlorates, chemically reactive compounds that are mildly toxic and corrosive. Perchlorates do not just coat a surface, they interact with it. The motors, the seals, the electrical contacts, the joints. Over months of exposure, the accumulation is not trivial. The life support systems face the same accounting. The International Space Station keeps its crew alive through a closed-loop environmental system that recycles almost everything, scrubbing carbon dioxide from the air, purifying urine into drinking water, managing oxygen levels continuously. It is the closest analog we have for what a Mars return vehicle would need to do. But the station operates in low Earth orbit, where resupply missions arrive regularly. If a carbon dioxide scrubber fails on the station, a replacement can be launched within months. If it fails on the return cruise, there is no replacement coming. The air becomes unbreathable in a finite and calculable amount of time, not a slow degradation, a deadline. The engineering response to this is redundancy, backups for the scrubbers, backups for the water recyclers, backups for the critical valves and sensors. Each backup adds mass. Mass requires more fuel to launch from the surface of Mars. More fuel requires a larger tank, or a longer in-situ production run, or both. Every backup you add feeds into the rocket equation that governs everything else. The mission planners are caught in a trap between safety and feasibility, and there is no obvious line where one ends and the other begins. The question that everything in this section is building toward is a simple one. Will a rocket that has sat on Mars for a year, in dust and cold and radiation, perform flawlessly when the crew ignites it? Not adequately, not approximately, flawlessly, because there is no such thing as a partial launch from Mars. The window is there, and then the window closes, and the crew will not get another chance to answer the question if the first answer is wrong. The orbital mechanics do not wait, the dust does not care, and the spacecraft racing toward a future Earth position will have been carrying both of those facts from the moment it left the ground. The question underneath all of that is deceptively simple. How much energy does it actually take to leave? Most people have an intuitive picture of the return. You are on Mars, you light the engines, and you fall back toward home. Earth is there, waiting. Gravity does the work. The return feels like a release, not an effort. That picture is wrong. Here is what actually happens. Earth orbits the Sun at roughly 30 kilometers per second. Mars orbits the Sun at roughly 24 kilometers per second. Those 6 kilometers per second are not a trivial difference. They define the entire energy budget of the return trip. When you launched from Earth and headed outward toward Mars, you were shedding velocity, slowing down relative to the Sun, falling into a wider orbit. The physics worked with you. On the return, you are doing the opposite. You are launching from a planet moving at 24 kilometers per second and trying to catch a planet moving at 30. You have to speed up. You have to gain that difference, plus escape Mars's gravity well, plus complete the orbital transfer burn that curves your path back toward Earth's position. Add those requirements together. The total delta V for the return trip, the total velocity change the engines must produce, often exceeds the delta V for the outbound journey. Not the same, more. The intuitive picture, the one where falling home feels easier, gets the physics exactly backward. That reversal has consequences measured in tons. SpaceX's Starship architecture for Mars anticipates needing approximately 1,200 metric tons of propellant just to launch from the Martian surface and complete the return journey. Picture roughly 10 blue whales stacked by mass. That is the fuel bill for one departure. It cannot be carried from Earth. The rocket equation forecloses that option completely, the same way it foreclosed carrying return propellant for the crew mission overall. The fuel must be made on Mars from Martian resources before the crew ever arrives, which brings the problem back to power. Making 1,200 tons of methane and liquid oxygen through in-situ chemical reactions requires enormous, sustained energy. Not for a day or a week, for months of continuous industrial-scale operation. And here is where the engineering trade-off becomes genuinely difficult. There are essentially two ways to generate that power on the Martian surface, and neither one is straightforward. The first is solar. Mars receives only about 43% of the sunlight that reaches Earth. It is farther from the Sun, and the inverse square law is unforgiving. Solar panels that would generate a given output on Earth produce less than half that output on Mars under ideal conditions. Conditions on Mars are rarely ideal. Dust settles onto panel surfaces continuously, coating them and cutting efficiency further. During a global dust storm, which can persist for weeks or months, output drops further still. A solar power system on Mars is variable, degradable, and vulnerable to the one weather event that the planet generates with some regularity. The second option is nuclear. NASA has been developing small fission reactors capable of producing tens of kilowatts of continuous power, regardless of sunlight, regardless of dust, regardless of storm season. Continuous and reliable, those are the two words that matter most for an industrial process that cannot pause. But reactors are heavy. They are mechanically and thermally complex. They require shielding, both for the electronics they power and for the crew nearby. And they carry political weight that engineering alone cannot resolve. Engineers must choose between a power source that is light and flexible but unreliable, and one that is reliable but heavy and contested. Neither option is clean. Every kilogram of reactor hardware feeds back into the launch mass, which feeds back into the fuel required to get that hardware to Mars in the first place. But the power source is only part of the problem. There is also the question of when all of this must work. The most common plan is to send the fuel production equipment to Mars years before the crew departs. Pre-positioned hardware, running autonomously, filling tanks slowly over months. When the crew lands, the propellant is waiting. The logic is sound. The risk profile is more complicated. What if a dust storm 2 years earlier degraded the solar panels beyond their recovery threshold? What if the drill rig sent to extract water ice from the regolith struck rock instead of ice, and sat idle, and the chemistry could not proceed without the hydrogen that water provides? What if a component failed in the first Martian winter, and no one was there to repair it? And the tanks are still empty when the crew touches down. The crew would arrive to find no fuel, not less fuel than expected. None. That is not a contingency buried in an appendix. It is a real and open risk, flagged by mission planners, with no fully satisfying answer. The answer most often proposed is multiplication. Send 2 fuel plants instead of 1. Send 3. Send multiple independent power sources. If one fails, the others carry the load. Redundancy at the level of entire facilities, not just components. The problem with that answer is familiar by now. 2 fuel plants weigh more than 1. More mass means more launch vehicles, more orbital assembly, more of everything that the rocket equation taxes. The third instance of this pattern in the mission architecture deserves its own recognition. The rocket equation does not care whether you are adding mass for the crew, for shielding, for backups, or for backup fuel plants. It charges the same compounding toll each time. Every solution that multiplies hardware multiplies the fundamental problem of getting that hardware off Earth. The delta V paradox does not end with the physics of velocity. It threads through the power supply, the chemical plant, the pre-positioning strategy, and the redundancy calculus. Each layer of the problem opens onto the next, and the mass of a solution to one layer becomes the seed of the next layer's constraint. The fuel manufacturing challenge may be the most solvable problem in the return sequence, given enough preparation time and enough pre-positioned hardware. But solving it depends on decisions made years before the crew launches, on equipment running unattended in an environment that has already proven itself hostile to machines, and on a margin thin enough that a single extended dust storm could erase it entirely. The crew will know whether the tanks are full when they land. They will not know until then, and what they find when they arrive will shape everything that comes after. And the object that makes everything possible, or impossible, is waiting for them already. It has been waiting for months. It sits on the Martian surface alone, exposed, in a silence no machine built on Earth has ever had to endure. Let's stand beside it for a moment before it fires. Every rocket humanity has ever launched left the ground surrounded by infrastructure. Launch pads engineered to absorb millions of pounds of thrust. Gantry towers holding the vehicle steady until the last possible second. Fuel trucks, weather stations, thousands of engineers watching thousands of readouts. Emergency teams ready to respond in minutes. If something went wrong before ignition, a crew could scrub, retreat, diagnose, repair, and try again. That entire system existed because it was possible to build it. Earth allowed it. The Mars Ascent Vehicle has none of that. Not a scaled-down version, none of it. It arrives on Mars attached to a lander. It is placed on the surface. And then it waits. Weeks pass. Months. Possibly more than a year. No technician checks its seals. No engineer inspects its wiring. No shelter keeps the temperature steady. It simply sits in one of the most hostile surface environments in the solar system, and it must survive that exposure without degrading. And then, when the moment arrives, it must fire perfectly. The first time. Because there is no second time. The environment it must survive starts with temperature. At the Martian equator, surface temperatures swing from roughly minus 125 degrees Celsius at night to around 20 degrees Celsius on warm afternoons. That is a range of approximately 145 degrees within a single day-night cycle. To put that in context, the most extreme temperature swings recorded anywhere on Earth in the deepest parts of Antarctica do not match it. Every seal in the MAV, every valve, every sensor, every wire must survive that cycling day after day without cracking or warping or losing its tolerance. Materials that perform well in Earth testing can fail under repeated thermal stress of this magnitude. And failure in a single seal does not mean a delayed launch. It means no launch. Then there is the dust. Martian dust is not like sand. It is extraordinarily fine, closer in texture to talcum powder, and it carries an electrostatic charge that makes it cling to surfaces and work its way into gaps that seem impossibly small. It contains perchlorates, chemically reactive compounds that are mildly corrosive to metals and electrical components over time. A global dust storm can last weeks. During those storms, the air above the surface turns rust-colored, and visibility drops nearly to zero. The MAV sits through all of it. Dust accumulates on sensors. It works into joints. It sits on electrical contacts. And the vehicle must still function after months of that infiltration. Then the data shifted. Even in the intervals between storms, in the quiet periods when the Martian sky is clear, the MAV is being damaged in a way that cannot be seen at all. Radiation from deep space passes through the vehicle's electronics continuously. Cosmic rays, high-energy particles accelerated by the same galactic events that strip the light from distant stars, strike individual transistors on individual chips. Sometimes when a cosmic ray passes through a semiconductor, it deposits enough charge to flip a single bit from 0 to 1, or from 1 to 0. Engineers call this a single event upset. Think of it like a random typo inserted into a document, except the document is the operating software of a rocket that is about to launch. Most bit flips land in memory locations that do not matter, but one bit flip at the wrong address in the wrong register at the wrong moment in the ignition sequence could crash a critical system. Not degrade it, crash it. The MAV must be built with radiation-hardened electronics, specifically designed to detect and correct these errors. And even then, the risk is not zero. The vehicle that has to survive all of this is not a large machine. The NASA concept design for the sample return MAV stands roughly 3 meters tall, about the height of a standard doorway, and has an empty mass of around 400 kilograms. It uses solid rocket propellant. That choice is deliberate. Solid propellant requires no pumps, no cryogenic liquids, no complex plumbing that could freeze or crack during months of thermal cycling. Once manufactured and loaded, it is stable across a wide range of temperatures. But solid propellant carries a cost that matters enormously here. Once it ignites, it cannot be throttled. It cannot be shut down. If something goes wrong mid-burn, there is no abort. The burn proceeds to completion regardless of what is happening above or below. For a crewed mission, the design changes fundamentally. A vehicle capable of lifting people requires far more propellant mass, and that means switching to liquid fuel, almost certainly liquid methane combined with liquid oxygen, produced via ISRU. Liquid propellants allow throttling and, in principle, abort options. But they require cryogenic storage, which means keeping propellant at extremely low temperatures, while the vehicle sits on a surface that swings 145 degrees every day. They require managing boil-off, the slow evaporation of cryogenic fuel over time. Every solution, introduces a new class of problem. The physics of Mars itself demands a completely different rocket architecture. Mars's gravitational pull is about 3.7 meters per second squared, compared to Earth's 9.8. That is roughly 38% of Earth's gravity. Less thrust is needed to lift off the surface, which is genuine relief. But the atmosphere that surrounds the MAV at launch is so thin that aerodynamic control surfaces, the fins and vanes that help steer rockets on Earth, are nearly useless. The air is simply too sparse to push against. The MAV must use reaction control thrusters, small engines firing perpendicular to the main thrust axis to steer during ascent. That adds complexity. It adds mass. And it adds components that must survive the same months of thermal cycling and dust exposure as everything else. The optimal ascent trajectory also looks different from anything launched on Earth. On Earth, rockets pitch over toward the horizon slowly and carefully, partly because atmospheric drag penalizes moving too aggressively through the lower atmosphere. Mars has almost no atmospheric drag to worry about. The MAV can pitch over toward the horizon much sooner, following a flatter arc, which is the most efficient path to orbit under Martian conditions. The engine nozzles themselves are shaped more like vacuum-optimized nozzles than sea-level nozzles, because the surface pressure on Mars is so low that the exhaust expansion dynamics more closely resemble the near vacuum of space than the thick atmosphere at Earth's surface. All of that is manageable. What comes next is more difficult to solve. There is no GPS on Mars. There is no network of ground stations tracking the ascent. The MAV carries its own inertial measurement unit, a combination of accelerometers and gyroscopes that track every acceleration and rotation from the moment of ignition. That system calculates position and velocity continuously, integrating each small motion into a running estimate of where the vehicle is. But inertial navigation accumulates errors. Small measurement imprecisions compound over time. Over the 10 to 15 minutes it takes the MAV to reach orbit, those accumulated errors can grow large enough to matter. Some mission architectures propose using Mars-orbiting satellites as navigation aids during ascent, giving the MAV external reference points to correct its inertial estimate. That helps. It also means the entire ascent depends on those satellites being in the right orbital position, functioning correctly, and in communication range. Another dependency. Another thing that could fail. And for a crewed mission, there is no launch escape system. On Earth, crewed rockets carry escape towers or ejection seats specifically designed to pull the crew away from a failing vehicle in the first critical seconds. Those systems require mass that a Mars Ascent Vehicle cannot carry. The mass budget is too tight. If something goes wrong at ignition or in the first minutes of ascent, the crew has no dedicated escape option. The reliability requirements for the MAV therefore exceed anything previously attempted in the history of crewed spaceflight. Not by a small margin, by a significant one. The trade-offs around vehicle staging add another layer of calculation. A two-stage rocket allows engineers to optimize each stage separately, dropping the weight of an empty first stage before the second stage finishes the climb to orbit. But more staging means more separation events, more mechanisms that must fire correctly in sequence. Single stage to orbit is simpler, and Mars's low gravity makes it more feasible than it would be on Earth. But it pushes propulsion performance to its limits. Neither option is clearly safer. Both carry costs. And the target orbit itself is a compromise. Low Mars orbit, at roughly 300 kilometers altitude, requires the least propellant to reach. But even Mars's thin atmosphere exerts enough drag at that altitude to cause orbital decay over weeks. The orbiting Earth return orbiter, or in a crewed scenario the waiting transit vehicle, cannot loiter there indefinitely. Higher orbits are stable for longer but cost more fuel to reach. Every choice closes another door somewhere else in the mission. The MAV is not the most complex machine humanity has ever built, but it may be the most unforgiving one. And it has to work the first time, after sitting alone in the cold, in the dust, under the radiation, for as long as it takes for the crew to be ready to leave. The rocket that carries them home will have had no one watching over it, and the crew that depends on it will only find out whether it survived when they climb inside and light the engine. That moment, the ignition, is not the end of the challenge. It is the beginning of the next one. The ignition is only the beginning. Now the MAV is climbing. It pushes up through the thin Martian atmosphere, trading altitude for velocity, pitching toward the horizon as the air thins around it. Within minutes, the surface falls away. The dust plains and the craters and the equipment left behind shrink into geometry, then into abstraction, then into nothing. The vehicle breaks into orbit, and waiting there, already circling, is another spacecraft. The Earth return vehicle has been in Mars orbit for months. It arrived ahead of the crew, positioned and ready, executing its own slow loops around the planet. Now the two spacecraft are in the same region of space, both moving at roughly the same orbital velocity, both trying to close the remaining distance between them and meet at a precise point with a precise matching of speed. This is orbital rendezvous. It is one of the most technically demanding operations in spaceflight. The reading came back reversed. We have done orbital rendezvous before. NASA and the Soviet Union both worked out the fundamentals in the 1960s. The Apollo program depended on it. Soyuz missions depended on it. The entire architecture of the International Space Station depended on vehicles meeting in orbit and joining without destroying each other. Those programs produced some of the most precise engineering achievements in history, but every one of those rendezvous happened in Earth orbit. And in Earth orbit, mission control was always present. Think about what that means in terms of time. A radio signal traveling between the ground and a spacecraft in low Earth orbit completes a round trip in about 2.5 seconds. That is slow enough to feel like conversation. Controllers can watch a docking approach in real time, call out corrections, issue abort commands, respond to anomalies as they develop. The crew hears back almost instantly. At Mars, the physics are different. At closest approach, a one-way signal from Earth to Mars takes approximately 4 minutes. When the planets are on opposite sides of the Sun, the delay stretches past 20 minutes each way. A round-trip message under those conditions takes more than 40 minutes. That is not a communications inconvenience. It is a wall. Mission control on Earth cannot watch a rendezvous unfold and intervene. By the time they hear that something has gone wrong, the problem has already resolved itself, one way or another. The rendezvous at Mars must therefore execute autonomously, not assisted by ground support, not supervised in real time. The spacecraft track each other using onboard radar or optical sensors, systems that measure relative position and closing velocity continuously. Onboard computers take that data, calculate the required thrust adjustments, and command the engines to fire. The orbital mechanics proceed without a human hand on anything. The approach is methodical. 2 kilometers out, the MAV is closing slowly, sensors locked on the waiting vehicle. At 1 kilometer, the approach rate is verified again. At 500 meters, the margin for error is measured in centimeters per second, not kilometers, not meters, centimeters per second. Too fast, and the collision is catastrophic. Both spacecraft destroyed. No debris salvageable, no mission. Too slow, and the vehicles drift past each other. The window for docking closes, and the MAV must spend precious fuel recalculating and reapproaching. If the fuel margin was already thin, that miscalculation can be the one that makes docking impossible. The spacecraft approaches within a few hundred meters of its only way home and cannot reach it. This is the ballet. 2 machines moving through empty space, deciding entirely on their own, with no conductor, no prompter, no one who can hear them in time to help. But the weight of it changes depending on what is aboard the MAV. In the sample return scenario, the stakes are scientific. A failed rendezvous means the loss of irreplaceable Martian material and years of mission effort. That is a profound loss. It is not the same as what a crewed rendezvous carries. If the crew is aboard the MAV during the approach, their lives depend on autonomous software and hardware performing flawlessly in an environment they have never been tested in before. There is no launch escape system. There is no second attempt if the docking fails and the fuel runs out. There is no flight controller who can see what the crew sees and talk them through it. There are 2 spacecraft, 2 sets of onboard computers, and the laws of orbital mechanics. The reliability standard that implies has never been met before. Not for a crewed spacecraft operating this far from Earth. executing a maneuver this precise, with no real-time oversight and no recovery option available. Every previous crewed rendezvous had a ground team watching. At Mars, the spacecraft are alone in the most complete sense. And the question that follows from that is not a comfortable one. Whether fully autonomous rendezvous can be trusted to perform at the reliability level a crewed mission requires, over the range of possible anomalies in Martian orbit specifically, is not yet answered. The technology exists, the orbital mechanics are understood. Whether the system can be made reliable enough, robust enough, tested enough to stake crew lives on it without ground oversight is a different question from whether it can be made to work in the best case. 2 spacecraft, a closing distance measured in meters, a precision margin measured in centimeters per second, and Earth, 4 minutes away at best, with no ability to hear what is happening until it has already happened. The docking either succeeds or it does not. And even a successful docking is not the end of the challenge. It is the beginning of the next one. The docking succeeds. 2 spacecraft, joined in orbit, begin the long drift home. And the word that matters most in that sentence is not joined. It is long. Stay with that silence for a moment. The successful instant is behind them. What lies ahead is months of nothing happening. Slowly. And in those months, quietly, without any single dramatic failure, the mission may become its most dangerous. The spacecraft that carries the crew home is not the spacecraft that left Earth. It has done 1 interplanetary transit already. It sat in space, and on or near the Martian surface for the better part of 2 years. Every seal, every valve, every battery, every spool of wiring has been exposed to thermal extremes and radiation for that entire time. It is, in the simplest terms, an older machine. Think of a long-distance runner asked to complete a second marathon of the day on the same legs, without rest, without resupply. That is what the return cruise asks of the vehicle. The life support system at the center of all of this is called the ECLSS, the Environmental Control and Life Support System. It scrubs carbon dioxide from the air the crew breathes, recycles water from humidity and from urine, regulates temperature and pressure, monitors trace contaminants. On the International Space Station, this system requires regular maintenance. Components are replaced on a known schedule. Spare parts arrive on cargo vehicles. The return cruise has none of that. No resupply vehicle will meet them. No supply of spare parts will reach them between Mars and Earth. If the carbon dioxide scrubber fails, the air becomes unbreathable in a finite, calculable amount of time. You must hope you packed a working spare, and that the spare has survived the same radiation and thermal cycling that degraded the primary, and that you correctly predicted which component would fail months before it did, when you were still on Earth deciding what to bring. This is the hidden weight of the return cruise, not a single dramatic failure. A slow accumulation of degraded systems, each one slightly less reliable than it was at departure. But the spacecraft is not the only thing aging. The crew's bodies have been changing since they left Earth. Bone density decreases in lower gravity, muscles atrophy. The cardiovascular system adapts to an environment where the heart does not have to work against the same gravitational demands. Some long-duration astronauts report vision changes, possibly from fluid shifts in the body, redistributing without gravity pulling it downward. Studies of astronauts returning from long ISS missions have found measurable changes in brain structure. Sleep is disrupted. Mars has a day roughly 24 hours and 37 minutes long, close enough to Earth that the crew could adapt. But the return cruise has no day-night cycle to anchor to. The body's internal clock drifts. By the time the return vehicle fires its engines and leaves Mars orbit, the crew is already tired, already stressed, already physiologically altered by months of lower gravity, radiation, and confinement. They are beginning the most demanding leg of the journey in the worst physical condition of their lives. And then comes the third quarter. Researchers who study isolated confined environments noticed a pattern years ago in Russian Mir missions, in Antarctic researchers spending winters at the South Pole. Morale does not collapse at the beginning, when everything is new and the challenge feels meaningful. It does not collapse at the end, when home is close. It collapses in the middle. Just past the halfway point, when the novelty is gone and the endpoint is not yet visible, when accumulated stress and monotony and isolation have had enough time to work. The dangerous period. The point when small irritations become genuine tensions, when the mission's purpose feels abstract, when the mind begins to turn inward in ways that are not productive. Scientists call it the third quarter phenomenon. Here is the duration context that makes this matter. Valery Polyakov, a Russian cosmonaut, spent 437 days aboard the Mir space station, from January 1994 to March 1995. It remains the longest continuous spaceflight in human history. He survived. He returned. He walked off the spacecraft under his own power, eventually. A Mars mission would be 800 to 900 days total, nearly twice as long, farther from Earth than any human being has ever been, with no rescue possible under any circumstances. No one has been where this crew will be. The record Polyakov set is not a proof of concept for a Mars mission. It is a lower bound, but the picture did not hold. There is a phenomenon that astronauts returning from low Earth orbit describe, a cognitive and emotional shift that happens when you see Earth from space as a fragile blue marble, small and alone against the darkness. They call it the overview effect. The planet looks different, precious. The distance creates a kind of clarity. Many astronauts describe it as one of the most profound experiences of their lives. The return from Mars inverts this completely. Each day on the return cruise, Earth grows slightly larger against the stars. Not a dot anymore. Growing. Home. Visibly closer than it was yesterday. And completely unreachable for months. Not close. Not almost there. Months away. The psychology of this has no precedent. You can see it. You know it is there. You know the people you love are on it, going about their lives at a distance that is closing, slowly, in ways you cannot control or accelerate. The nearness of something you cannot reach is a different kind of torture than pure absence. Researchers who study Mars mission psychology flag this as one of the less studied and potentially more dangerous stresses of the return leg. The communication lag compounds all of it. At the start of the return cruise, a one-way signal from the spacecraft to Earth takes approximately 20 minutes. A conversation is not a conversation. It is an exchange of recorded messages, question and answer separated by 40 minutes of waiting. By the midpoint of the journey, the lag drops to a few minutes. Only in the final weeks does communication approach anything resembling normal, real-time exchange. Think about what a 20-minute one-way delay means in a personal crisis. If a crew member's parent becomes seriously ill on Earth, the news arrives 20 minutes after it was sent. The reply arrives 20 minutes after that. If someone dies, the notification is already 20 minutes old when it lands. The funeral will happen before the crew member can respond, cannot attend, cannot comfort family, cannot do anything except sit in a metal tube tens of millions of kilometers away, watching the delayed record of events they had no ability to influence. This is not an edge case. Over 800 to 900 days, statistically, something will happen to someone the crew loves, and the crew will be unable to do anything except continue the mission. There is no good answer to this. There is only preparation and acceptance. Psychological screening tries to select people with strong coping mechanisms and stable support networks. Compatibility testing attempts to pair crew members whose personalities will not grind against each other after months of confinement. Conflict resolution training gives the crew tools for managing the interpersonal friction that will accumulate when the same small number of people share the same small space for years, when trivial habits become unbearable, when the sound of someone chewing or humming or breathing at a particular rhythm becomes genuinely maddening. Private sleeping quarters, curated entertainment, movies and books and music, and possibly virtual reality environments are all under consideration as mitigation. But you cannot fully prepare for something that has never been done before. That is the honest statement. The screening, the training, the private quarters, the entertainment systems, all of it is based on analogs. Mir, Antarctic winter stations, submarine deployments. None of those analogs is a Mars mission. None of them involves 800 to 900 days. None of them involves being genuinely unreachable by anyone on Earth for the duration. The long-term cognitive and biological effects of that much time in deep space, that far from rescue, are not fully understood. The psychological models are extrapolations. Good extrapolations, built by serious researchers, but extrapolations nonetheless. And what happens when the extrapolations turn out to be wrong is not a question anyone has answered. The spacecraft drifts home. The crew endures. And the planet ahead of them, growing slowly larger each day, is still months from being real. The planet grows larger each day. Not dramatically, not visibly, hour to hour, but measurably, undeniably, in the way that a destination begins to resolve out of abstraction and into something real. The psychological weight of that shift is its own subject, but the mechanics of arrival carry a different kind of weight entirely. Because reaching Earth is not simply a matter of pointing toward it and waiting. The spacecraft has been traveling for 6 to 9 months. It has covered approximately 200 million kilometers, and the target it must hit is not Earth. The target is a corridor in Earth's atmosphere roughly 2 degrees wide. To understand how the crew even knows where they are at this stage, you have to understand the deep space network. The DSN is a system of 3 antenna complexes positioned around the world. 1 in California, 1 in Spain, 1 in Australia. Each facility is positioned roughly 120 degrees apart from the others, spaced that way deliberately, so that as Earth rotates, at least one facility always has a clear line of sight to deep space. There is no gap. There is no dead zone. The network keeps watch continuously. Here is how the tracking works. A massive antenna on the ground transmits a signal to the spacecraft. The spacecraft receives that signal and responds. The time it takes for the signal to travel out and back, combined with the shift in frequency caused by the spacecraft's motion, gives engineers 2 pieces of information: position, velocity. The measurement is extraordinarily precise. Across hundreds of millions of kilometers, the DSN can pinpoint a spacecraft's location to within a few kilometers. That is not a rough estimate. That is a few kilometers out of 200 million. The DSN supports dozens of active missions simultaneously. The Mars rovers send their data through it. The Voyager probes, now beyond the solar system, still communicate through it. A crewed Mars return vehicle would receive priority over those other missions, but the dependency remains. There is one deep space network. It is a single point of failure for every deep space mission humanity currently operates, crewed or otherwise. That fact sits quietly in the engineering plans, unresolved. As a backup to radiometric tracking, the spacecraft carries a star tracker. This is a camera that photographs the surrounding sky, compares what it sees to an onboard catalog of stellar positions, and calculates the spacecraft's orientation from that comparison. It is celestial navigation, the same method sailors used for centuries, automated and made precise enough to operate at interplanetary scale. Together, radiometric tracking from the ground and optical navigation on board give the crew and mission control the best possible picture of where the spacecraft is and where it is going. But here is where it gets strange. All of that precision, all of that continuous tracking, all of that redundancy exists to thread a corridor that barely exists at all. The spacecraft approaches Earth at approximately 11 kilometers per second. That is roughly 40,000 kilometers per hour. After 6 to 9 months of travel and 200 million kilometers of distance, the vehicle must enter Earth's atmosphere at an angle that falls within a band less than 2 degrees wide. Think about what 1 degree looks like. Hold your hand out at arm's length. Look at your pinky finger. The width of that finger, held there, covers roughly 1 degree of sky. The entry corridor is twice that, after 200 million kilometers, at 40,000 kilometers per hour. And the consequences of missing it are not survivable. If the approach angle is too shallow, shallower than about 5.5 degrees below the horizon, the spacecraft skips. The atmosphere deflects it back out like a stone skipping off water. The vehicle bounces into an elliptical orbit around Earth, with no fuel remaining to correct the trajectory. Not a rescue scenario, not a recoverable contingency. The crew would be in orbit with no means of coming down. If the approach angle is too steep, steeper than about 7.5 degrees, the deceleration forces exceed what the human body can withstand, or the heat shield fails under the thermal load. The vehicle burns up like a meteor, completely. There is no version of too steep entry that ends with a safe landing. The corridor between those two outcomes is 2 degrees wide, not slightly constrained, brutally constrained, and the crew is arriving at 40,000 kilometers per hour. This is why the final weeks of the return cruise are defined by continuous recalculation. Mission Control takes in every scrap of tracking data the DSN provides, refines the trajectory model, and prepares a sequence of trajectory correction maneuvers, TCMs, brief thruster firings that adjust the vehicle's path, compensating for accumulated drift. The crew has been performing TCMs throughout the return journey, but the final ones carry the most consequence. The fuel remaining at this stage is the last available. There is no reserve beyond what these final maneuvers consume. Every burn must count. The astronauts strap in. They run through checklists they have rehearsed dozens of times. They check life support, verify entry configuration, confirm communication with mission control. The planet in their windows has shifted from a bright point to a disk, and from a disk to something recognizable. Blue, white, the particular colors of a world that contains water and weather, and the only breathable air any of them have ever known. Entry interface is defined as 120 kilometers altitude. That is the point where the atmosphere first becomes dense enough to produce measurable drag on the vehicle. Once the spacecraft reaches that boundary, the physics take over. No further corrections are possible. The thrusters cannot overcome the forces involved. The trajectory is fixed. The next 20 to 30 minutes determine whether the crew survives. Everything built in the preceding years, every kilogram of propellant produced on the Martian surface, every component that held together through the dust and radiation and cold, every maneuver executed correctly, every system that kept working without spare parts and without resupply, all of it has led to this corridor, 2 degrees wide, over 200 million kilometers of travel. At a speed that makes the question of a few decimal places in an angle calculation the difference between home and oblivion. The entry has not yet begun, but the margin for error has already closed. Let's follow them through it. The spacecraft crosses 120 kilometers and the atmosphere bites, not gently. The air at that altitude is almost nothing by any measure that would matter to a person breathing it. But at 11 kilometers per second, almost nothing is more than enough. The shockwave builds in front of the heat shield, compressing the air faster than it can move out of the way, heating it to roughly 5,000 degrees Celsius. That is not the temperature of the heat shield itself. That is the temperature of the air in front of it. The heat shield surface reaches approximately 3,000 degrees Celsius, glowing brighter than molten lava, radiating light in the visible spectrum, a streak of fire crossing the sky above Earth. The heat shield is not simply a barrier. It is an ablative system, meaning it is designed to slowly burn away. The material, in modern designs made from pica, phenolic impregnated carbon ablator, or a compound called AV coat, undergoes pyrolysis under that heat, chemical decomposition from temperature. The outer layer vaporizes, carrying the heat away with it in the outflowing gas rather than conducting it inward toward the crew. Engineers sometimes describe this as the shield sweating to stay cool, using its own destruction to survive. The ablation rate must be tuned precisely. Too fast, and the material is consumed before entry completes. Too slow, and the heat conducts through to the structure behind it. The picture did not hold. Mars return is not the same as returning from the International Space Station. A spacecraft returning from low Earth orbit is moving at roughly 7.8 kilometers per second. A spacecraft returning from Mars is moving at 11 to 12 kilometers per second. That difference sounds modest. It is not. Kinetic energy scales with the square of velocity. The difference between 7.8 and 11 kilometers per second is not a 40% increase in energy. It is more than double. The total thermal energy a Mars return heat shield must manage can exceed 100 gigajoules. That is the equivalent of approximately 2.5 tons of TNT, or roughly one typical American household's total annual energy use, released in 15 to 20 minutes across a heat shield, only a few meters in diameter. The SpaceX Dragon uses Pica X, a refined version of the same material, for returns from low Earth orbit. A Mars return vehicle would need significantly more ablative material, which adds mass which feeds back into the rocket equation, which tightens the propellant margins on the Martian surface, which is a loop this mission has been threading since the beginning. And then there is the part that no one can help with. The ionized plasma surrounding the capsule during peak heating blocks radio waves. Mission control loses all telemetry. The spacecraft disappears from every screen. Signals cannot pass through the plasma sheath in either direction. For several minutes, the crew is unreachable and untrackable. There is a monitoring room somewhere on Earth where engineers sit and watch nothing, because nothing is what the instruments are able to show them. The crew is alone inside a fireball, decelerating at forces that compress the chest and narrow the vision, with no one able to hear them, and nothing anyone could do if they could. The deceleration during a return from the moon ran to 6 or 7 G, sustained across several minutes. A person massing 70 kilograms at 7 G experiences the equivalent of 490 kilograms pressing down from every direction. The chest compresses. Blood is forced away from the brain. Vision narrows toward grey and can fail entirely. Astronauts train for this in centrifuges, learning to tense the muscles of the legs and abdomen, to breathe in controlled patterns, to resist the slow fading of consciousness. The crew returning from Mars has already spent the better part of 3 years in space. Their muscles are weakened. Their cardiovascular systems have adapted to environments without gravity. They are attempting to endure forces that would tax a fully conditioned body, in bodies that have been slowly unmade by the journey. The failure modes are not theoretical. In 2003, the Space Shuttle Columbia broke apart during re-entry. A piece of foam insulation had struck the thermal protection system during launch, creating damage invisible until re-entry revealed it. Hot plasma entered through the damaged area. The vehicle did not survive. All 7 crew members were killed. Columbia was returning from low Earth orbit. Not from the moon, not from Mars. The thermal stress it faced was a fraction of what a Mars return entry would impose. A defect in a heat shield designed for Mars return, a flaw in manufacturing, or a small impact during the long cruise home would allow temperatures that no material aboard could survive. The crew would have no warning and no time. Beyond the heat shield, the sequence of failures that can kill continues. The parachutes deploy in stages, drogue chutes first to stabilize the capsule and slow it to subsonic speed, then main parachutes, tens of meters in diameter. Too early and the aerodynamic forces shred them. Too late, and there is no altitude remaining for them to work. The separation of the heat shield and the deployment of the chutes are triggered by pyrotechnic charges, small explosive devices that must fire in exact sequence at exact moments derived from altitude, velocity, and acceleration sensors. All of it automated. All of it unrepeatable once begun. In 2020, a Soyuz capsule landing with cosmonauts aboard deployed one of its parachutes incorrectly. The crew survived a harder than normal landing because the backup systems functioned. A crew returning from Mars, already weakened and possibly disoriented, after months of re-entry deceleration preparation, might not survive what those cosmonauts survived. Landing itself is a choice between 2 imperfect options. Ocean landings, as in the Apollo missions, offer a forgiving surface, a capsule that floats, and recovery ships positioned nearby. The risk is a capsule that flips inverted in the water, leaving crew trapped. Land landings, used by Soyuz and available in Orion and Dragon configurations, require accurate prediction of touchdown sites and rely on small retro rockets firing at the last seconds to cushion the final impact. Neither is clean. Both place demands on a system that has been operating for 3 years without resupply or repair. When it ends, if it ends without incident, the hatch opens. The crew emerging from a Mars return capsule will not step out under their own power. Astronauts returning from 6-month missions aboard the International Space Station are routinely carried from their capsules. Their muscles have atrophied. Their cardiovascular systems have deconditioned. Their inner ears, adapted to weightlessness, send balance signals that no longer correspond to what the body is experiencing. Mars returnees are coming back from a mission 2 to 3 times longer. They may be barely conscious. They will need to be shielded from direct sunlight, their skin and eyes unprepared for unfiltered natural exposure after years in controlled environments. They will need hydration, medical assessment, and a long, gradual reintroduction to the gravity of the world they came from. They will be welcomed home as heroes. They may not be able to stand, and that is not the end of the reckoning. Long-duration spaceflight does not stop affecting the body when the mission ends. It changes gene expression. It alters immune function. It disrupts the microbiome. Scott Kelly and his identical twin brother Mark offered the closest study science has yet conducted. Scott spent nearly a year aboard the International Space Station, while Mark remained on Earth as a genetic baseline. After Scott returned, approximately 7% of his gene expression changes had not returned to his pre-flight baseline 6 months later. His telomeres, the protective caps on chromosomes that shorten with age, lengthened during the mission in space, then shortened rapidly after he came home. The biology did not simply reverse. Some of it persisted. Some of it may persist indefinitely. A Mars mission would be longer than Scott Kelly's year in orbit. The radiation dose would be higher. The physical demands would be greater. The returning crew would face increased cancer risk, possible immune dysfunction, potential accelerated aging in some tissues, and effects that current science cannot yet predict, because no one has been where they will have been. They will require medical monitoring for years after landing, perhaps for the rest of their lives. The body that crossed 200 million kilometers and came back is not the same body that departed. The mission changes them at a level deeper than memory or experience. It changes them at the level of cells. This is part of what going to Mars and returning actually costs. Not in fuel, not in dollars, in biology, in years, in the quiet, ongoing reckoning that continues long after the cameras and the crowds have gone.